Hello and welcome to Nand To Tetris. My name is Shimon Shoken and I'm a professor of computer science at IDC Herzliya and visiting professor at the Hebrew University of Jerusalem.
Hi, I'm Noam Nissan, a professor of computer science at the Hebrew University of Jerusalem and a researcher at Microsoft. Together, we'll teach this course.
And the first thing that we're going to want to do in this unit is to give you the overall picture of what this course is all about. Well, in this course, we're going to build a complete general purpose working computer from the ground up, hardware and software. And we are going to divide this huge enterprise into two separate courses. In the first course, which is going to be 7 weeks long, this course, we're going to build the hardware of the computer. And in the second course that will be offered later, we are going to complete the picture and build the software hierarchy that sits on top of the computer that you will build in the first course. So that's what we're going to do in the next 7 weeks. We're going to focus on building the hardware of a computer, which we call hack. So it's going to be a great journey consisting of 7 weeks, 6 projects, 1 computer, and 0 prerequisite knowledge. We assume no knowledge whatsoever in computer science or engineering. Everything will be given to you in the course itself. So this has been our first unit in Nand To Tetris, and coming up is the road ahead, a more detailed description of what we're going to do in this course.
We're going to start this course by describing the main mental tools that we're going to use in this course, and in fact the main mental tools that computer science uses all the time that will allow us to design an extremely complicated artifact step by step. Many of you have probably taken a programming course. Many of you may have not, but many have. Usually, in such a course, in the first class and the first lesson, you start looking at a very, very simple program, sometimes called Hello World. And this is a program that just prints Hello World on the screen. Usually, you start discussing the various fluff around the commands, basically stating, oh, here's the program, and this is how it's supposed to be written. You talk about various commands in the program. For example, the 4th line or the 5th line in what you see in front of you basically tells the computer to print a string Hello World on the screen, and that's really what the program does. And you discuss all that things, and that's how you start a programming course, a Programming 101 course. Now, when you think about that, that's very problematic. There are a lot of things that are under the hood here. First of all, there's this amazing thing. What you see as a program is just a bunch of letters. So, for example, if you have the P letter, this is a letter P. It's not doing anything, it's just a letter. And in fact, we know that in computers, the letter P is represented by a number, and turns out to be 112. So you have a number 112, and then you have a number 114 for R, and so on. And somehow these letters are supposed to do something? How does that happen? Well, you are told something about compilers that translate it to a different language, and the other language a computer hardware can execute, but how does that work? How does it even work? All that is swept under the rug when you start introduction to computer science or to programming. Similarly, if you look at even the simplest program, the simplest command, for example, print Hello World. How are you supposed to do that? Printing Hello World on the screen actually involves setting a bunch of pixels on your screen to be more lighter or darker. And it's a lot of pixels, and you have to actually put the pixels that are lighter in a very special order to somehow represent the letter H and then the letter E. How is that? Does all that happen? That's an extremely complicated thing, and yet you just use it. That is also swept under the rug. Again, you're told about standard libraries and operating systems that do all that for you, but you don't really worry about them. Why don't we have to worry about them? The main secret of computer science is the fact that you really don't have to worry about them. You can really start and do Programming 101, as many students have done throughout the years, without worrying about all these very basic questions. How does that happen? How come you don't need to worry about how? Because it's enough to worry about the what. It's enough to know what the programming language is supposed to do, and you don't need to worry about what happens behind it, because you're only using it, you're not now actually trying to duplicate it. The how of something is called the implementation. How do you actually make it happen? That's called to implement it. The what is called the abstraction. That is, if you tell the computer language is supposed to do such and such, you don't need to worry about how it is done, but the such and such, the exact specification of the such and such, that's the abstraction that we have, that's the interface that you get to work with, and you only need to worry about that when you actually program. When you are taught in Programming 101 that you actually can run that program, the whole point is that you only need to worry about the abstraction, that when you write that command, it's supposed to write hello world on the screen, and the whole point is that you don't need to worry about how that is done. It's enough to know what it does. This is not a bug in the way that we teach programming languages. It's actually the main point of programming languages. Don't worry about the rest. Just worry about what it's supposed to do and trust that someone else worried about the how. So you may worry here, is this a scam? So if no one worries about how something is done, people are only enjoying the nice things that are done, how is it ever going to be implemented? Who is going to worry about the how? Well, it could be someone else, which is always nice to know that someone else can do that. It could be you, later or earlier. If it's later, you don't need to worry about it now, which is very nice, because now you can focus on the task at hand, which is using the programming language. Even if it was you earlier, that you already implemented the programming language in the past, this allows you to forget. It allows you to forget all the details, all the work that you put into actually implementing it, and just remember what is the thing that you did. So it's an extremely important thing, and that's the most potent tool of computer science, that once we can separate concerns, we can forget a lot of details about implementation and only remember a very clean a very clean interface, a very clean description of what is done there, then you get this mental saving of not having to have everything in your mind at the same time. You can repeat that many times and many different multiple layers of abstraction, one above the other. So for example, suppose we have already built the blue stage box. We can forget its implementation, worry only about its interface when we try to implement a green box above it. Once we've finished with the green box, we can forget its implementation, worry about only the interface when we implement the orange box above it. When we finish that, we can forget again the implementation when we try to implement a purple box above the interface of the orange box. This way, we have multiple stages, each one of them very simple, and yet at the end we get a fantastically complex artifact composed of many simple stages. This is exactly what we'll do in this course. Here is a high-level description of the different abstraction layers we have in this course. We start with very basic, simple gates. We build more complicated chips from them, and from them we build even higher, more complicated chips like a CPU, and then we put them into a computer, and that continues as a software layer that we'll cover in part 2 of the course, where we build more and more complex software artifacts above these hardware artifacts. Every week, we will worry about a single level of abstraction. We take the lower level as given. We only remember what it does. We forget how we did it. We implement the higher level of abstraction, the next level of abstraction. We test that it works. And then, presto, we finish the week. We can move to the next week where we already know that this level works very well. So the lower level we can take as given in the next week because we just finished implementing it. The next level, we are going to actually guide you, give you very explicit guidance how you're going to implement the next level of abstraction, given the fact that you have already have the previous one. And then we also give you a testing suite that allows you to really test that what you did this week works, so that you can be sure that next week everything will keep on functioning. So by the end of the course, what have we achieved? By the end of the course, after a few weeks of actually every week building upon the previous layer, we get a complete functioning computer. A computer that starts with very basic building blocks called NAND gates, which are very, very simple logic gates, and ending with a computer that can run almost any program, for example, the Tetris that gives this course its name. In the process of doing it, you've gained a lot of very important computer science tools. First of all, you gained the experience of working with abstractions. You've gained an experience of working with the main working horse of computer science at every point in time, forgetting about what you don't need to remember about the how, and working about the next level of abstraction. This is the main thing we always do as programmers, and you've experienced it. You also, by the way, once you did all these different steps, you learned at every step what you need. And the different steps in building a computer are the interesting pieces of information you need to know, you need to understand in order to understand how a computer is actually constructed. And at the end of the day, you sort of now have a complete understanding. You have built a complete functioning computer. You understand all the levels. So finally, the myth of how a computer works is no longer mystical. You understand it. All this accomplishment is going to happen in 14 weeks. And in two parts. In the first part of the course, which is what we currently have on Coursera, which is going to last 7 weeks, we're going to build the whole hardware platform of a computer. We're going to start with a very simple logic NAND gate, and we're going to create a computer that can run assembly machine programs. And this is what you do in the first part of the course, 7 weeks, 7 different steps, each step very simple, and you get a working hardware platform. In the second part of the course, which is going to be called, non-surprisingly, From Nand to Tetris Part 2, we're going to start with the same hack computers that we've built in the first part of the course and continue adding a software hierarchy that will allow us to actually run any type of application that we write in a high-level programming language. For example, an application like Tetris that gives this course its name, but also any other type of application that you may want to write. The second part of the course is not available on Coursera yet. If you really, after doing this course, you cannot wait for it, you can always go to our book, which has all the information, including part 2, and keep on working directly from the book. What we're going to do in the next 2 units is explain a little bit more, talk a little bit more about the roadmap ahead, which tells us, first of all, what are we going to do in this course in the hardware part, what are the main steps that we're going to do, and then also what are the main steps that are going to be done in the second part of the course. And after that, in the next week, we'll actually start going step by step.
In the previous unit, Noam gave you an overall description of the Nand to Tetris journey. In this unit, we're going to focus on what we're going to do in this course, which is building a computer called Hack. So here's the computer in a very broad description, or sort of a diagram that captures only some of its very main elements. It's going to have a ROM, a CPU, a RAM, and many other chips. And once we build this computer, we're going to connect it to a standard keyboard and to a display unit. And at this point, you can start executing programs and enjoy the computer that you actually built. Which kind of programs? Well, anything that comes to your mind. You can write a program that plays Pong, or a program that plays Space Invaders, or Sokoban, or of course Tetris. And these are actually examples of programs that were previously written by students who took this course. So here's the general picture of this course, and I'm basically repeating things that Noam said before. We start with some general idea of a program that we want to write. We write the program, we compile it, we translate it further into a machine language, we load the code into our computer. The computer is going to use all sorts of chips that we built, which are based on elementary logic gates, and the whole thing ends up with the hardware itself. So basically what we did is we built a software hierarchy that sits on top of some hardware platform. And as Noam explained, we decided to split this enterprise into 2 different parts. The first part is called Nand to Tetris Part 1, and the second one, which will be offered later, is called Nand to Tetris Part 2. And in this particular course, we're going to focus on the hardware only, beginning at the very low level of the hardware itself, of electronics and logic gates, and we're going to do it bottom up. So Here we are at the very low level of everything in applied computer science, and this actually is not computer science. This is electrical engineering and solid state physics and so on, and all sorts of things that neither Norm and I understand much about. And therefore, we're going to abstract away this hardware and focus instead on the most elementary logic gate that we can think of, which is called NAND. You know, NAND is something that I can describe in 10 seconds, and I will do it in one of the following units. But for now, let us assume that it's simply a basic logic gate. We take this NAND gate, and from it, using a certain art called combinational logic, we're going to build a whole set of elementary logic gates like AND, OR, XOR, and so on. Then we will take these gates, and from them, we're going to use both combinational logic and sequential logic, which is a different art of design which takes into consideration times and time and clocks. And from it, we're going to build things like registers and RAM units and CPU. And then we'll take this chipset that we built and we'll design from it a full-blown computer architecture called HACK. Now, in order to write programs that can execute on this machine and do it in a convenient way, we're going to also introduce an assembler into the picture, and we're going to develop also an assembler for the HACK machine language. Now, I've introduced all sorts of concepts that may sound very unfamiliar. Don't worry about it. Everything will be explained as the course progresses. Now, many of you are probably wondering, how are we going to actually build all these chips? Well, as it turns out, hardware engineers today don't do anything with their bare hands. They develop computers using computers. And in particular, they use something called hardware simulator to design and test and debug the hardware that they want to build. And that's exactly what you will do also in this course. What we see here is a screenshot of our hardware simulator, a piece of software that you're going to download freely from our website, and then you're going to install it on your computer, and you will do all the projects in this course using your computer and software that we will supply. So let us give you an example of how we're going to actually do it. Here's an example of a XOR chip, which is one out of about 30 different chips that we're going to build in this course. And what you see here is an abstract description of how XOR operates. So basically, you're going to take this abstraction, think about it, and along with all sorts of tips and guidance that we're going to provide, you will come up with some logic diagram that enables you to build XOR using lower level gates that you built before. Then you will take this diagram and specify it using a language that we will teach you, which is called hardware description language. The result will be something called HDL program. You will take this HDL program, you will combine it with some test scripts that we will provide, and then you will debug, test, and complete your HDL program using the hardware simulator that I described before. So that's what we're going to do with every one of the chips that we're going to build in this course. And the result is going to be the HACK computer. Now we're going to separate this journey into 6 different projects. So let me say a few words about every one of them. In the first week, we're going to build some elementary logic gates, 15 gates altogether, as you see here in the slide. In the second week, we're going to build an arithmetic logic unit, an ALU, which is the centerpiece of the CPU that we will build later. In the third week, we're going to build memory systems, starting with registers and going all the way up to RAM and ROM units. In the fifth week, we're going to take all the chipset that we built so far and use it to design an actual computer. In week 4, before we build the computer, we will write some programs in the HACK machine language in order to get a feeling of what this computer is going to do. And in the last week in the course, we're going to introduce an assembler for the HACK machine language and actually develop it in 2 different ways. One for people who have background in programming and one for people who don't. So these are all the projects that you're going to work on in this course, and the result of your effort is going to be the hack computer, a general purpose computer that can run any program that comes to your mind, Tetris and practically anything else. Now, I'm sure that many of you are wondering, what do I have to know in order to take this course? Well, the answer is we assume no previous knowledge whatsoever in computer science, engineering, or mathematics. All the necessary knowledge that is required to build the computer and to take this course is going to be supplied in the course itself. This is a self-contained course. You're going to learn a lot in 7 weeks of exciting projects. So this has been the unit in which we describe the journey from NAND to the hack computer. And in the next unit, we're going to overview the journey from the hack computer to Tetris.
In the last unit, you heard about what we're going to do in this course in part 1 of the course. Now I'm going to very shortly tell you what still remains for the second part of the course, for Nand To Tetris part 2, that is not currently offered. Well, in the first part, in this course, you're going to start with very simple NAND gates, as you've heard, and you get all the way to a working computer system on which you can run any program, for example, Tetris, that gives this course a name. So what remains? What are we going to do in the second part? Well, the question is really the kind of programming that one does on that computer. In the computers that we're going to finish building in this course, you're also going to build a computer language that you can run on it, but it's a very low-level assembly language. If you look at the assembly language, it does not look nice. It's certainly not what you start using in programming 101 courses. It's a very low-level language, very inconvenient. Most programmers, they really want to work with a high-level language, something like this, the example, that is very typical of what you see in an Introduction to Programming course. So the kind of things that you have in such high-level language includes a rich language, loops, data types, methods, abstraction, many things that do not appear in the assembly language that is the end of this course. Also, there are many high-level operations, for example, math operations, for example, input and output operations that are primitive and are expected by any programmer that wants to write to print hello world and expect hello world to appear on the screen. And in fact, in the second part of the course, where we deal with the software hierarchy, this is exactly what we're going to implement. We're going to present a high-level language called Jack, and we're going to write a compiler for it, using several layers of abstraction, of course, because that's a complicated thing, building a compiler. Similarly, we're going to build a standard library and, in fact, a mini operating system that gives you all the high-level services that programmers expect. Once you have these two things, then you're basically at the starting point of an Introduction to Programming course, because you have a high-level language that you can use normally, and now this hopefully closes all the gap between the very basics of how computers are built, all the way to how the programming language and operating system and standard library that you expect to get as a introductory computer programmer. As we said, part 2 of Nand To Tetris is not yet offered. We plan to offer it in the future, but if you cannot wait, it's already ready in the website and in the course book. In the next unit, we just we will tell you a little bit about the first project, or actually the zeroth project, which just wants to make sure that you're up to date, you found our website, you know how to submit exercises in Coursera, and once we finished with that, the next week, we actually start with building the computer. So today we're starting our journey of actually building a computer. You've probably all heard that computers internally only have zeros and ones. And the reason that they only have zeros and ones is because that's what they can get away with. It's simplest to have only two possible values that you need to maintain, and that's going to be enough, as we will see today. We're starting with the completely theoretical, logical kind of analysis of how to deal with zeros and ones. And later in Unit 3, we'll actually talk about how these abstract 0 and 1 signals directly are implemented as chips inside a computer. So let's talk about the abstract 0 and 1, on and off, true or false, not, no and yes, 0 and 1. In general, we can use all these names to refer to each one of two different physical values that are maintained somewhere in the system. We will use 0 and 1 for the rest of this unit, but that's completely general. So what can we do if we only have zeros and ones? Well, we can do some kind of basic operations on them. For example, the AND operation takes two 0, 1 signals and returns 1 only if both of them were 1. So if you have 0 and 1, the result is 0. But if you have 1 and 1, the result is 1. We can actually see all the different possibilities for combining two values of zeros and ones into the result, which is the AND of them, in a little table that is called the truth table, because it actually gives all the different possibilities of the inputs of x and of y, and for each one of these possibilities, it lists what is the output, what is x and y. So AND is one of the possible operations. Here's another very popular one, or it returns 1 if any one of the two inputs is true, is 1, or even if both of them are 1. The only time it returns a 0 is if both x and y are 0. And here's a third interesting operation. This one is a unary operation. It only takes a single input bit as input, x, and returns the opposite of it. So returns for if the input is 0, the output is 1. If the input is 1, the output is 0. So these are possible, very simple operations on Boolean numbers, sort of like addition and multiplication and maybe other kind of operations are operations on integers or on real numbers. These are operations on Boolean numbers. Once we have operations, we can start combining them just like we combine arithmetic operations in arithmetic formulas. So for example, let us try to evaluate what would be the expression of not 0 or 1 and 1. Notice that we have parentheses to give us the priority here. So the way we evaluate is very simple. We know how to evaluate 1 and 1, which is 1. So the whole thing simplifies to not 0 and 1, or 1. We know how to evaluate 0 or 1. That's going to be 1 because it's an OR operation. So that's equal to not 1. And now we know how to evaluate not 1. That's simply 0. All very simple, and we can do that. Now, once we know how to evaluate Boolean expressions over values, over 0, 1 values, then we can actually get general expressions, general functions that takes indeterminates x, y, z as inputs, and for each value of x, y, z, produce an output. So for example, I can define a function of 3 inputs, x, y, and z, that basically tends x and y, or not x and z. And look in the parentheses to see the priorities that I was thinking about. Of course, I could define any other function by any other Boolean formula, and that would give me a function. If we want to know what kind of function is that, well, we can actually list all the possible values of x, y, and z, and for each one of them, try to write down what is the value of the function. The really nice thing about Boolean values is the fact that there are only a finite number of possible inputs, and we can actually list each one of them. This is completely different from functions that you've learned in third grade, where you have functions from integers to integers, and there are infinitely many integers, so you can never write down the function in a complete specification of all the possible values. But here we can actually write down all the possible values that the triplet x, y, z can have. We can have x0, y0, and z0 that corresponds to the first row in the table, and so on, until the last row of the table that corresponds to all three of them being 1. Now, for each one of these rows, we can just evaluate the function, what is the function f of x, y, z defined by the previous formula for these values. For example, let's look at the second row. In the second row, we have x equals 0, y equals 0, z equals 1, and we can just plug in the numbers 0, 0, 1 into the formula. Every time we have an x, we put a 0 there. Every time we have a y, we put a 0 there. Every time we have a z, we put a 1 there. And now we just get a formula with constants in it, and we can evaluate it just like we did in the previous slide, and we can figure out that that is 1, that the second row should get a value of 1. We can do this similarly for each one of the possible rows, and we can completely fill the table. And now notice that this table of values completely gives you the same information as the previous expression did. It completely specifies the function, the Boolean function that we just had. The first way we described the function was as a formula. The second way we described the function was as a truth table. And these are two completely identical definitions, ways to describe the same Boolean function. So now, once we know we can describe Boolean functions using formulas, and basically we have general Boolean expressions, we can actually try to find what are a bunch of Boolean identities that always give us equality. For example, we can always see that x and y, whatever the values of x and y is exactly equal to y and x. This is called the commutative law. We have a similar phenomena for x or y equals y or x. So these are like commutative laws that hold for these Boolean algebra, in this Boolean algebra. There are a bunch of other kind of identities. For example, the well-known associative law. If you have x and y and z, it's the same thing if you first do x and y, or whether you first do y and z. Similar thing happens for or. Another well-known law is a distributive law. If you have x and y or z, that turns out to be exactly equal to x and y, all that, or x and z. Now, as opposed to the usual arithmetic, where we only have a distributed law of multiplication over addition, here we have both the distributive law of and over or, and the dual law of distributive law of or over and. The same trick works if you want to do x or y and z, that's x or y and x or z. Now there are also laws called De Morgan laws that govern how knots work, how they interrelate with and or. These laws are called De Morgan laws, and they say the following interesting thing. If you take x and y and do a knot on all of that, that's equivalent to first doing knot of x and oring that to knot of y. And we have the dual one that if you have knot of x or y, that's exactly equal to knot of x and knot of y. Now, all these laws can be easily proved, if you wish, not if you wish, really proved by simply listing all the possibilities in a truth table and verifying that they get the same truth table for the left-hand side and the right-hand side. Now, there are a bunch of other laws, and we can use them to actually do manipulations on Boolean algebra. So, for example, once we have a formula, for example, the formula that you see here, not of not x and not x or y, for example, it could be any other formula, we can now start applying some of these identities to change its form, to simplify it, or to just to bring it into a different format. So, for example, the first thing we can do here is look at the second part, at the last sub-expression, the not x or y. We can use De Morgan law here and basically convert it to not x and not y. Now, if you look what we have here, we can use the associative law. Because we have not x and not y, we can change the order of doing the and. And we get another expression which is identical using the associative law. At this point, we have something really interesting at the beginning. We have not x and not x. That can be just simplified to not x. Why is that? Because we can actually see also, that's another identity that we didn't explicitly list, but it's easy to verify in the same way that if you take any value w, in our case w is not x, and do w and w, that's completely equivalent to w. Now, this is called the idempotence law, and we can thus simplify the previous expression by simply removing one of these w's, one of these not x's. Now, we're ready to use De Morgan law again. And now we got into not x or not y. Now again, here's another law that we didn't list explicitly, but you obviously all know that not x is always equal to x. So using double negation law, we can simplify that to x or y. So that just gives you some kind of demonstration that you can basically just manipulate Boolean expressions, sort of like you manipulate arithmetic expressions in elementary school. There's another way to get the same conclusion, the same equivalence, without actually going through these algebraic manipulations, simply by actually looking at the truth table. We take the expression, we build the truth table for it, and we've already seen how to take an expression and find its truth table, and then we get the truth table that you see on the board. Now, once you have this truth table, you can say, I know this truth table. This is exactly the truth table of the OR function. And then that immediately proves that the expression on the top is completely equivalent to x or y, as we've derived using algebraic methods previously. Now, of course, it's not completely, you won't always be so lucky to do some kind of big truth table and recognize what it is and immediately see a better and nicer and simpler expression that gives you the same table. Sometimes you will have to do algebraic manipulations, but on the other hand, it's not always true that algebraic manipulations are easy to do in the sense of finding a very simple expression. So, but in general, in principle, you can use both of these methods to actually simplify Boolean expressions or find alternative forms that give you the same Boolean expressions. So we've just finished our first unit describing how to manipulate logical values. Notice that we're still keeping our abstract point of view of just logical values and not thinking about any physical realization that we will have inside our computer. In the third unit, we'll actually switch our point of view and start talking about these same kind of phenomena, but from the point of view of real chips and real gates that we have inside a computer. But before we get to that, in the next unit, we'll keep maintaining our theoretical point of view and start talking about the following problem. How can we construct a function from basic operations? How does that, this is exactly the kind of things we will need to do when constructing hardware. We know what it wants to do, but we'll have to actually construct it from Boolean operations, and we'll try to see how that is done, first from a theoretical point of view in the next unit. So in the last unit, we talked about what are Boolean functions, Boolean values, Boolean algebra, Boolean formulas. What we want to do now is actually talk about how we can construct Boolean functions from more primitive operations. So we already saw two ways to represent a Boolean function, a Boolean expression and a truth table. We also already know how to go from the expression to the truth table. You take the expression, evaluate it for each possible values of the input bits, and then you can fill the truth table. What we want to do now is exactly the opposite. You start with a description of a function, let's say given as a truth table, and our challenge is to come up with a formula that computes the same Boolean function. Why do we need to do that? Well, that's exactly what we have to do when we come to design a computer. We know what we want to do, we know what we want a certain unit to do, but then we actually have to compose it from primitive gates, from primitive operations. So let's see how we can do it. So again, we continue with our abstract treatment. We're trying to see what is the basic logical way we can actually construct such a Boolean function from primitive operations. Later, once we actually talk about practically constructing them, we will be more practical oriented, we will go step by step and so on. At this point, we just want to make sure what are the principles. So let us start with a specification of a Boolean function given as a truth table. How can we construct it? Well, here's what I'm going to describe to you is a standard way of what's called constructing a disjunctive normal form formula for it, and it goes like this. We actually go row by row in the truth table. We focus only at the rows that have a value of 1. For example, the first row here has a value of 1. Now what we can do is we write an expression that basically gets a value of 1 only at this row. For example, so in particular, since here in this row the values of x, y, and z are 0, 0, and 0, if we look at the expression not x, and not y, and not z, that is going to be a Boolean function, the green Boolean function, that only gets a value 1 on this row. So now we have one Boolean function. We do the same thing, we construct another Boolean function, another clause, for each row that has a value of 1. So for example, there's another second row with a value of 1. This time, in here, this row, y equals to 1, while x and z equal to 0. So the clause we write here is not x, and y, and not z. Again, this is something that completely gets the value of 1 only on this row, and gets the value of 0 everywhere else. We do that for every possible row that has a value of 1. Now the purple row. Now we have a bunch of different functions that each one of them gets a value of 1 only at its row, and gets a value of 0 in all other rows. But we desire a single function, a single expression that gets exactly the value 1 exactly on all of these rows and 0 on the other rows. How do we do that? Well, that's very simple. We just OR them together. And now we get a single expression, a single Boolean function that gets value 1 exactly on the rows for which we built clauses for, and gets 0 everywhere else. And now we've basically constructed our function as a Boolean expression, only using ands, nots, and ors. Now, of course, course, once we have this expression, we can start manipulating in various ways. This is one way to write the function as an expression, but if you actually look at it, you can see that we can start changing its format. For example, if you look at the first two clauses, you can see that one of them is not x and not y and not z, while the other is not x and y and not z. Notice that we have both possibilities for y and exactly the same fixed value for x. So instead of these two clauses, we can combine them into one clause, which does not ask about y, and only asks about not x and not z. So we get an equivalent expression that's slightly shorter. There are more manipulations that we can do, let's not go into them, but we can actually write the same expression in many different ways. Some of them will be shorter than others. Some of them might be more efficient in terms of when we actually go to implement them in a computer. But the point is, logically, they're all completely equivalent. Now you might wonder, how do you actually find the shortest or most efficient formula that's equivalent to the one we've just derived? Well, that's not an easy problem in general. It's not easy for humans, nor is there any algorithm that can do that efficiently. In fact, this is an NP hard problem to actually find the shortest expression that's equivalent to a given one, or even to verify if the expression that you're given is just a constant 0 or 1. What's more interesting, what I really want to focus at this point, is that we've really proved a really remarkable mathematical theorem, that any Boolean function, it doesn't really matter on how many variables and what the Boolean function is, can be represented in an expression using only the operations and, or, and not. Now, to notice how remarkable that is, just think about Boolean functions on integers functions that you've learned in elementary school. Not every function on integer numbers can be represented using, let's say, addition or multiplication. In fact, most functions cannot be represented just by arithmetic operations. Yet, because of the finite world that we live in the Boolean algebra, every Boolean function can just be represented with and, ors, and nots. And that is exactly what gives us a basic power to actually construct computers only with these possible gates, only with these possible operations and, or, and not. But do we really need all of them? Well, here's a better theorem if you wish. We don't really need OR gates. Just with ands and nots, we can construct any Boolean function. How can we prove that? Well, we already know that if we have ORs, we can do everything. We've just seen that. And now the only thing that we need to show is that we can actually compute an OR with AND and NOT gates. But we know how to do that already. We recall De Morgan formulas that exactly give us a formula for OR that only uses NOT and AND gates. So now we have a really more remarkable theorem that we only need these two basic operations to actually compute every Boolean function. Can we go even less? Can we give up, let's say, the AND gate? Well, that doesn't make sense because NOT only takes one value to one value, doesn't even allow us to combine anything. Can we give up the NOT gate? Well, not really, because AND has this property that if you only feed it zeros, it will always have 0 as output. And there are Boolean functions that when you feed them 0 give you 1 as output, so AND by itself wouldn't suffice. But it turns out that there is yet another operation that by itself does suffice to actually compute everything. So let me introduce the NAND function. So the NAND function, here is a truth table. It gives 0 only if both of its inputs are 1, and every other possibility it gives 1. Logically, x NAND y is defined to be the negation of x and y. So what's so remarkable about this Boolean function? Well, the nice thing is that we can prove the following theorem, that if you only have NAND gates, you can already compute every Boolean function, you can already represent every Boolean function as an expression using just these NAND gates. How do we prove that? Well, we know that if you can do not, and if you can do and, you can do everything. So we just have to show how to do not with NAND gates and how to do and with NAND gates. So here's how you do not. If you just look what happens when you feed x to both inputs of the NAND gate, you plug it into the truth table in the previous slide, and you can see that not x is really represented by x NAND x. That's part one. The second part we need to show, how do we do and? Well, x and y turns out to be not of x NAND y. But how do we have not? Well, we've just seen that you can do not with NAND itself. So now we've basically reduced the fact, instead of using nots and ands, we're just using NAND gates. And we got our amazing theorem that just if you have a NAND gate, you can compute everything. And this is exactly what is going to be our approach when we actually go to build a computer. We will give you a primitive NAND gate operation, and you will basically build the whole computer, all the complicated logic that we'll actually ask you to build using just from these basic NAND operations. So at this point, we've just finished our abstract point of view about Boolean logic, and now we're doing a really interesting shift of perspective from the abstract logical operations to the actual gates and the actual gates from which we build computers. This switch really there's no actual difference between the two different things in terms of the kind of things that we do, but it's just in the way that we're thinking about them. Until now, we asked you to think about everything as abstract Boolean logic. From now, we're going to start asking you to think about everything as actual little pieces in a computer that compute the functionality that we want.
In the previous 2 units in this week, we talked about Boolean functions, and most of this discussion has been theoretical. Starting with this unit, we are going to talk about how we actually implement these Boolean functions using hardware. In particular, we're going to talk about a general technique called gate logic, which, loosely speaking, it's a technique for implementing Boolean functions using logic gates. Now, what is a logic gate? Well, a logic gate is a standalone chip, or a very simple chip, or an elementary chip, which is designed to deliver a well-defined functionality. Something like NAND functionality, AND functionality, OR, and so on. What is a composite logic gate? A composite logic gate is one which is made up from elementary logic gate and other composite logic gates. Or simply, it's a more complex gate than the elementary ones. And in this course, we'll develop things like multiplexers and adders. And obviously, most of you don't know what these terms mean. Don't worry about it. You will get acquainted with them and actually build them in the next few weeks in the course. All right, so let us begin with the most fundamental logic gates that we use in this course, called NAND. Here's the definition of a NAND. This is actually the standard diagram that we use to describe a NAND gate. It has 2 inputs and a single output. Everything here is binary, so A, B, and out are either 0 and or 1. Here is a functional description of this gate. If both inputs are 1, we output 0. Under any other circumstance, we output 1. And here's also a truth table description of the same functional specification. Any one of these descriptions is fine. Taken together, what we have here is an abstraction of the NAND gate. We didn't say a word about how this thing is actually working. We just describe what kind of functionality we can expect it to deliver. Okay, moving forward, here are three classical gates that pop up in every digital design project. We have an AND gate, which outputs 1 when both its inputs are 1 and 0 elsewhere. We have an OR gate, which outputs 1 when either one of its inputs are 1 and 0 elsewhere. And we have a NOT gate that operates as a converter. And we can put these gates together to create more complex functionality, as we'll illustrate later on. In particular, we can use these gates to create composite ones. So, for example, here's a three-way AND, which is an extension, if you will, of the simple two-way AND. And one way to build it is to use this trick here. We can take the output of one AND and feed it into one of the inputs of another AND gate. And if we wire everything correctly, this gate is supposed to deliver the required functionality. What we see in the dashed line rectangle around the implementation is a documentation of the interface of this chip. So the user lives outside the dashed rectangle. So the user sees only the three inputs and the output, as you see in the left-hand side of the gate description. If you want to go in, or to sort of open up the black box, you have to see what is documented and done inside the dashed rectangle. So with that, I would like to say a few words about the notion of interface and implementation. The gate interface is the gate abstraction. You know, this is how the user thinks about what the gate is supposed to do. Interface answers the question, what? At the same time, if you want to understand how the chip is doing what it's doing, you have to go deeper and go in, well, I'm not sure that deeper is the right word, but you have to go to another level of detail in which you actually, the black box opens up and you see how the chip is actually constructed. Or you do it yourself, you know, if your job is to be the person who is actually realizing this abstraction. Now, the interface of the gate is unique. There's only one way to describe the gate's functionality. Otherwise, you know, if there's more than one way, either you're not describing it well, or you're confusing the user, because, you know, there should be only one unique way to describe what a gate is supposed to do. At the same time, there may be several different implementations that realize the same abstraction. And some implementations may be, you know, more elegant, they may use less energy, they may be less or more expensive, and so on. So one abstraction, many different implementations. This is very typical in computer science. Whenever you build a large system, you have this, this duality. All right. Now, abstraction. Now, the interface of the gate is unique. There's only one way to describe the gate's functionality. Otherwise, you know, if there's more than one way, either you're not describing it well, or you're confusing the user, because, you know, there should be only one unique way to describe what a gate is supposed to do. At the same time, there may be several different implementations that realize the same abstraction. And some implementations may be, you know, more elegant, they may use less energy, they may be less or more expensive, and so on. So one abstraction, many different implementations. This is very typical in computer science. Whenever you build a large system, you have this duality. All right, now moving along, so we talked about the gate interface and the gate implementation. Let's talk about something known as circuit implementations. If I want, I can realize these gates using hardwired circuits like this one. And there's a certain sort of graphical language here that describes what's going on. When we want to represent the fact that the gate outputs 1, we assume that a light bulb will be turned on. And when the gate delivers output 0, the light bulb will be off. So if we look at this implementation of an AND circuit, we see that because of the architecture of this circuit, the light bulb will be on only if the both relays are latched. Under any other circumstance, the light bulb will go off. And that's exactly what I want to do when I represent the AND logic. What about OR logic? Well, once again, if I have to build a circuit implementation of OR, I can realize it using this particular architecture. And here it takes only one latch to close the circuit and turn on the light bulb. And once again, this is consistent with the desired abstraction of an OR circuit. Moving along, here is a circuit implementation of a 3-way AND. And you can easily, I think, convince yourself that it will deliver the required functionality. And yet I want to remind you that earlier in this unit, we also presented this implementation of an AND gate, if you recall. So I'd like to say a few words about these two different approaches to designing hardware. And I want to start by saying that in this particular course, we don't deal with physical implementations. And therefore, this whole discussion of circuits, transistors, relays, and so on, all this stuff, and what you see in the top left corner of the screen here, this is electrical engineering. It's not computer science. And the people who build these gates using circuits and similar technologies, some of them are far more advanced and sophisticated, well, these people are called electrical engineers. God bless their souls. We have enough problems in computer science to worry about, so we are not going to worry at all about physical implementations, and all the designs that we are going to use in our course are going to be similar to what we did here at the bottom right of the screen. We are going to take existing logic gates, beginning with NAND, and beginning with NAND only, and we're going to piece them together in some clever ways in order to generate and produce the required functionality. So this has been a unit in which we gave you a first brief introduction of logic gates. And in the next unit, we are going to introduce to you a language, some sort of a programming language called HDL, or hardware description language, with which you can actually build logic gates like the ones you saw in this unit, and far more complex logic gates and chips down the road. In previous units, we talked about how Boolean functions can be realized using logic gates. And in this unit, we're going to talk about how we can actually build and implement the logic gates using a formalism called hardware description language, or HDL. Once you build a logic gate in HDL, you can actually simulate it, test it, and finally build it in hardware, as we now turn to describe. All right, so let's begin this journey from abstraction to implementation. The first thing that you have to do as a gate architect is demand a full and complete description of the desired gate's behavior. And in this case, what we need is some sort of a truth table. In the case of XOR, it's a very simple truth table. And the truth table, along with the gate diagram, gives you everything that you need in order to understand what this chip is supposed to do. And what we see here is also sometimes called the chips interface. And indeed, using this information, you can start writing an HDL file that will look something like this example here. So we start the HDL program, or the HDL file, with some documentation free form. You can write whatever you want there, which describes what the gate is supposed to do. And then we specify the name of the chip, the names of the inputs of the chips, and the names of the chip's output. And all this information, by the way, the name of the chip and the names of its inputs and outputs is typically given to you. It's not something that you decide. It's something which is part of the chip's contract, if you will. So you simply write it up using the syntax, and then you write the magic word parts, which describes that here begins the segment of your program in which you're going to describe how this chip is actually designed. Now, when you use such a chip, such a XOR chip, what we've seen so far is called the gate interface. And notice that this is everything that I need in order to use XOR gate. However, if I have to build this gate, well, that's a different story. Now I have to open up the black box and actually design it. So when we use chips, we always wear two different hats. There's the hat of the programmer who uses the chip as a chip part, and for this all we need to know is the chip interface. And there is the other hat of the chip's builder, which is what we're going to do now. So moving along, let's discuss how we actually build this chip from scratch. All right, so actually we are not going to build it from scratch. We can, if we need to, we can build it from NAND gates only. However, let us assume that we've already built an AND gate, an OR gate, and a NOT gate. Well, if we built these gates, or if someone gave us these gates that we can freely use, here is what we can do. We can inspect the truth table and figure out from the truth table that the XOR functionality can be described as follows. I mean, look at the truth table. The gate outputs 1 in 2 cases only. If A and not B, or if B and not A. That is, if A is true and B is false, or if B is true and A is false. This sort of comes out, jumps out from the truth table, you can either see it on your own, or as Noam described in one of the previous units, you can synthesize this, this insight or this Boolean function from the table itself. So once you come up with this insight, the next thing that you do is you think about it for a little while, and you come up with a gate logic diagram that describes how we can build this Boolean function using basic logic gates that we already have to our disposal. Now, developing such diagrams is a matter of experience, and the only way to gain this expertise is to see many examples like this one. So let's take this example and explain it in detail. So the first thing that we can do is draw the boundary of the chip diagram, or the gate diagram. So we use this dashed outline for this purpose, and what remains outside the boundary is the user's view of this gate. In other words, the gate interface. All the user knows is that he or she has a gate that has two inputs, A and B, an output called out, and altogether somehow this chip, as if by magic, delivers the XOR functionality. So we draw this diagram and this interface, and now we can delve more into the inner architecture. So notice how the A signal is being copied and sent simultaneously into two different destinations. One of them is the AND gate, and the other one is a NOT gate. This is perfectly okay in chip diagrams, and we see that the B signal undergoes the same treatment. And in general, when you write HDL code, you are allowed to take any signal and distribute as many copies as you want of this signal into as many destinations as you want. This wiring or these dispatching is done simultaneously. So to use a formal language, HDL has unlimited fan out. You can fan out any given signal to as many destinations as you want. And we do it, we always do it when we write HDL code. All right, moving along, notice that we're using some off-the-shelf gates, AND, NOT, and OR. Now, whenever you use an off-the-shelf gate, you are bound to use the names of the gate's input and output as advertised, so to speak. In other words, when you take the gate off the shelf, the gate comes along with what can be called the gate signature or the gate's API. So we have no degrees of freedom here. We have to use the official names of the inputs and outputs of every one of our chip parts. Now, the next thing that we do is let's focus on the red connections that we see here. These are the connections that we draw in order to connect the different chip parts together. Now, the rule is that every one of these connections has to be named, and it's our responsibility to come up with sensible names. So that's what we do. We can call this particular connection NOT A, which is a sensible name, I think, a self-descriptive name. We'll do the same thing with NOT B. We can call this one A and NOT B. We can call this one NOT B, NOT A and B. And that's it. We have named all the internal connections in our architecture, and we can actually now move on to describe this diagram in HDL. So now we can actually move on and implement this diagram using HDL. So we return to the HDL stub file that we had before, and I use the term stub file to describe a partial HDL implementation, so to speak, that actually describes only the chip's interface. And typically it comes with the statement implementation missing or put your code here and so on and so forth. So this is the contract that we actually have to implement. And now, indeed, we are going to focus on the implementation section of this file. And basically what we do is we begin to describe the gate diagram one chip part at a time. And for each one of the chip parts that we have, we write a single HDL statement that describes the chip along with all its connections. So we have we happen to have two NOT chip parts, so we describe them. The first NOT has in equals A. This is the input. The in input of the chip receives the A signal, and the output of the chip goes into NOT A. We do something similar with the other NOT chip. Then we describe the two N chips, and finally we describe the OR chip. Notice, by the way, that I use the words gate and chip interchangeably, and that's perfectly okay. A gate for me is simply a simple chip. All right, so this HDL diagram is nothing more than a textual description of the gate diagram. Did I say HDL diagram? I meant the HDL file is a textual description of the gate diagram that we see at the top of the slide. Now, I'd like to notice that once again we have interface, we have implementation, and also note that the interface of the chip is unique. There's only one way to describe this chip, and this is typically given to us by whoever commissioned us to implement this chip. At the same time, the implementation is not unique, and the same interface can be implemented typically in many, many different ways. For example, in the case of XOR, we can implement the XOR chip using 3 logic gates only. So, and it doesn't really matter how exactly we do it. You can think about it on your own if you want. But in general, there may be different implementations, and some of them will be less expensive. They will contain less chip parts, less connections, consume less energy, and so on and so forth. So the interface is unique, and the implementation varies. Now, I'd like to use this opportunity to make some general observations about HDL. And for ease of reference, I have placed in front of you what we saw earlier in this unit, the gate diagram on the right-hand side and its HDL description on the left. So what can we say about HDL? First of all, we see that there are certain issues in HDL which are very similar to what we normally do in other programming languages. We have to worry about good documentation of our HDL program, just like we do when we write a program in Java or Python. We have to come up with good descriptive names, both to the chips that we use and to the connections that we create within the architecture. So readability is terribly important. We have to make sure that our HDL code is self-descriptive and readable. And in order to do it, we also use indentation, and make the code look real nice. So all these things are expected from you when you write your own HDL programs. In addition, there are certain things which are really unique to HDL. First of all, HDL is a functional or declarative language. There's no procedure going on. There's no program execution going on. It is nothing more than a static description of the gate diagram. At the same time, we assume that at some point this descriptive code will go into some interpreter. Will go into, in our case, into a hardware simulator that can actually take this description and start to pipe values from the bottom all the way to the end. So we assume that there is some agent that will turn this implementation into something that is actually working. But this procedural part is not part of the HDL code. It's external to the HDL code. So because HDL is a functional language, we can actually write those HDL statements in any order that we wish. It doesn't matter if you begin to describe the NOT gate or the OR gate. It's completely up to you. But it is typically it's customary to begin to describe your diagram from left to right, and this also makes the code more readable. Also, note that each time we use an off-the-shelf gate, we commit ourselves to using the gate interface, that is, the names of the inputs and outputs that come along with the gate documentation. Now, in the hack computer that we're going to build in this course, we decided as a matter of convention to almost always use the letters A and B for a two-input chip and out for a single output chip. And therefore, we are going to have many chip connections that look like A equals A and out equals out. Now, at the beginning, this formalism, these conventions will look a little bit strange. What does it mean, A equals A, out equals out? If you think about it a little bit, and if you go back to consult these diagrams, you will see that these connections make a lot of sense, and actually they are very convenient from a programming perspective. You will realize that once you get your hands dirty and write some HDL code of your own. So I'd like to end with some comments about how the description languages in general. There are many of them out there, and yet the two most popular HDLs that at least I know of are VHDL and Verilog. These are the languages which are used, I think, in 90% of hardware design projects, but there are many other HDLs out there that can be used as well. Our own HDL is very similar in its spirit to the industrial strength HDLs that I mentioned earlier, VHDL and Verilog, and yet it is a very minimal and simple version of these HDLs, and for this reason you can master it in something like 1 hour of reading a tutorial and beginning to write some HDL code of your own. And most importantly, our HDL, along with our hardware simulator, gives you everything that you need in order to build the computer described in this course, and actually any other computer that you may want to build using the knowledge that you will gain in the Nand To Tetris course. So if you want to read more about HDL, and you should, take a look at Appendix A in the textbook, and also read the HDL survival guide in our Nand To Tetris website. Both are actually available in the website. And you may want to also take the hardware simulator tutorial and learn how to actually read HDL descriptions and execute the underlying logic of these HDL using simulation. So this has been the unit in which we gave you a primer of HDL, and in the next unit we'll describe once again how you and you may want to also take the hardware simulator tutorial and learn how to actually read HDL descriptions and execute the underlying logic of these HDL using simulation. So this has been the unit in which we gave you a primer of HDL, and in the next unit we'll describe once again how you can take your HDL designs and bring them to life within the context of the hardware simulator. In the previous unit, we learned how to implement a gate logic using HDL. However, nothing in what we did guarantees that the HDL code that we wrote is actually correct. We have no idea if this architecture that we put together delivers the intended results of the chip that we seek to design. So in this unit, we will close this gap and we will learn how we can take an HDL program and verify to the best of our ability that the program or the HDL file delivers the intended functionality of the underlying chip. Now, here is the big picture of what we're going to do. Given that we have a particular HDL file and we want to test it, we can load it into a special program called the hardware simulator. We have written such program and made it available to you in our website. This program happens to be written in Java. And this program is designed to simulate and test HDL files. So we load it into this program. We interactively test all sorts of operations on this chip, and we call this mode of testing interactive simulation. Alternatively, we can write another file and using a special language that we designed, which we called a testing language, something that you can learn in a few minutes, we can put together a set of replicable tests that are predetermined. So we don't have to do things interactively. We can think ahead of how we can systematically test the underlying chip. We write it in what is called a test script, and then we load into the simulator two separate files. We load the HDL code, we load the test script, and then we send the simulator to work. The simulator goes through every step in the test script and subjects the HDL code to the specified tests in this supplied script. We call this mode of operation script-based simulation. And finally, if we want, we can record the output of the simulation on something called an output file, and we can even compare the results of the simulation to a desired output, which is stored in yet another file called compare file. So, as you see, there are many new concepts and techniques involved in this practice of hardware simulation. And the purpose of this unit is to make all this new information concrete by walking you through a step-by-step process of testing a working example that will accompany us throughout this unit. Now, throughout this unit, we are going to present several software tools, actually just one software tool, the hardware simulator, and you are more than welcome to stop the video, invoke this hardware simulator on your own computer, and make sure that what we do can be done also on your machine. You can do all this if you have downloaded the software suite at the beginning of the course, and if so, the hardware simulator should be available on your computer, and everything that we do in the lecture can be done by you as well. So we encourage you to kick tires as much as you please. So let's go on and start with some concrete examples. So here's the example that I'm going to use throughout this unit. It's an HDL file describing the XOR chip that we talked about in the previous unit. So the code itself should be familiar to you, even though it's not terribly important for understanding this particular unit. All right, so once again, the fact that we wrote this very nice piece of code does not imply in any way that the code is actually correct. In fact, most likely it contains some errors, either syntax errors or logical errors or whatnot. So how do we test it? Well, here's what we can do. We can invoke the hardware simulator. The program starts running. We can load the HDL file into this simulator, and we can then enter zeros and ones into the A and B inputs and observe what is going on inside the chip. Now, how do we observe what is going on? Well, we have to tell the simulator to evaluate the chip's logic. The simulator will not do anything until we tell it to actually consider the new inputs that we entered and evaluate the chip's logic. And if we do this, the simulator will take these values, these zeros and ones or whatever we entered, and will kind of pipe them through the architecture. And at some point, something will come out from the output pin of the chip. So at that point, we can inspect what actually materialized. So we can observe the outputs of the chip, in this particular case, the value of the out pin. And if we want, we can also inspect the values of the internal pins, pins like not B, not A, and so on. And the simulator gives us all these nice capabilities. In particular, here's an example or a screenshot of the hardware simulator in action. And the simulator contains or features several different panes. So let's talk about each one of these panes in isolation. First of all, at the bottom left of the screen, we see the HDL code that we have loaded into the simulator. This is a static view. We cannot manipulate or edit this code. If we want to edit anything, we have to use an external text editor, change the HDL code and reload it. So this pane just gives us an idea of what is it exactly that we loaded into the simulator. Here we can actually interact with the input pins of the simulator. We can click them and change the values. We have 4 different possibilities of zeros and ones in this particular example. This is a very simple chip. And once we do this, we can click this icon, which looks like a calculator. And once we click it, we basically tell the simulator to evaluate the chip's logic on the supplied inputs. At this point, the simulator will spin its wheels. It will take a fraction of a second, and something will come out. We can then evaluate the output of the chip. In this particular case, we have only one output called out. And once again, if we want, we can also inspect the current values of the internal pins. So altogether, this GUI gives us everything that we need in order to carry out sort of hands-on interactive simulation of a XOR chip, or any other chip for this matter. All right, moving along, I would like now to give you actually a hands-on example of the hardware simulator in action. So let's do that and then go back to the lecture. This is the hardware simulator, and in order to use it, we have to first of all load an HDL program into the simulator. And we do it by clicking this icon here. So let us do it. And we see that we are in the Nand To Tetris folder. So within this folder, we're going to select projects. And within projects, we'll select project 0. And we see that we have a single HDL file here. So let us select it. This is the XOR file that we discussed before. And we loaded the chip into the simulator. Now, the pane at the bottom left, right here, gives me a display of the file that I just loaded. I can scroll back and forth. It's not separate. It's not terribly useful, but this pane is actually just a read-only display. There's no way to actually change the code when you are inside the simulator. If you want to change the code, you have to do it using an external text editor, and then you have to reload, of course, the file that you changed and saved elsewhere. So let us assume that we are happy with this file, and I want to actually simulate the chip logic. Well, I do this by, first of all, looking at the current input values, and we see that the default values of the A and B inputs of the XOR chip happen to be 0. So if I want, I can go ahead and change one of them or both of them to some other values. So let us change A to 1, and let us change also B to 1. And notice that nothing yet happened. In order to see how the chip responds to these changes, I have to reevaluate the chip logic. And I do it by clicking this icon here, the calculator icon. So let us do it. And we see that once we click this icon, the output becomes 0. And indeed, XOR of 1 and 1 is 0. If we want to see some other possibilities, we can once again manipulate one of the input pins, click the calculator, and we see that the XOR now emits 1 instead of 0. Another thing that we can do is inspect the values of the internal pins, which gives us yet another level of scrutiny, in particular when we try to debug the chip and understand why it is misbehaving for some reason. So this has been a very brief description of the first thing that you do when you use the simulator. You load the chip, you play with the input pins, you inspect the outputs and the internal pins, and this is the ABC of chip debugging and testing. I wish to remind you in closing that if you want to change the chip logic, you have to edit the HDL file using some external text editor, save the new file, reload it into the simulator, and rerun the tests in order to test the new chip design. Now, interactive simulation is very nice indeed, but at some point it can become rather tedious, especially if you have lots of bugs in your design, and each time you have to go through the same set of tests and so on and so forth. So with that in mind, we are fortunate that we also have the notion of a test script available to us. So here, once again, is the tested chip, and by the way, I allow myself to use the words chip and gate interchangeably. For me, a gate is simply a simple chip. So this is the tested chip, and here's an example of a test script designed to test XOR gate. Now, let us go through the test script kind of line by line. The first command in the test script instructs the simulator to load the XOR HDL file into the program. So even this step is taken care of. We don't have to do it ourselves. The test script will load the program for us. By the way, this is terribly important if you do repetitive debugging, because how do you debug a gate? You use an external text editor, to change the gate, and then you click save, and you go back to the simulator. So it's important to remember to reload the new version of the edited chip. So that's why we added this command to the test script. Now, once the HDL is loaded into the simulator, the test script begins a process of subjecting the chip to 4 different tests. The semicolon represents the ending of one particular test, if you will. And so we set the input values of the chip to 0 and 0. We evaluate the chip logic and observe the results. And then we go through the next test and so on and so forth until we complete all the possible, all the input possibilities for this particular chip. So this is how we carry out script-based testing, and it has many benefits. And far and foremost is the fact that we don't have to do anything laboriously, using our own intuition, because everything is predetermined. We have a set of replicable tests, and we just use the same tests over and over whenever we debug the chip, which can be 2 weeks or 2 months from now. So it's good to know that we can always repeat the same set of tests. So altogether, we will try to always use a test script. And the good news is that you don't really have to worry about how to write test scripts, because we are going to supply to you all the test scripts that you need in order to test the chips that you are going to design in HDL. So you worry about the HDL, and we are going to worry about the testing of your work. Another thing that we can do is keep track of the outputs of the simulation. So in particular, we can augment our basic test scripts with something like the following commands. We can, at the beginning of the test, when we initialize things, we can instruct the simulator to create an output file, which in this example we happen to call XOR.out. And as we go through the testing, at the end of each test, we tell the simulator to output to the output file a set of values which is determined in the preamble of the script. So as you see, the third line of the script says the output list is A, B, and out. And so whenever the simulator will see the directive output, it will write to the output file the current values of A, B, and out. And at the end of the simulation, we can simply inspect the result of the output file and convince ourselves that the chip has actually behaved according to expectations. In fact, in this particular example, if you will inspect the output file that emerged from the simulation, you will notice that it is completely identical to the truth table of XOR gate. So it looks like the gate is well behaving. So here's a snapshot of the hardware simulation in action using a test script. And once again, we have the HDL code as we did before at the bottom left of the screen. But we now have something new. We have a test script which can be seen on the right pane, which is some sort of a multi-purpose GUI area which we use for different purposes. And after we load the script, we can instruct the simulator to actually execute the script. We do it by clicking this control. And the simulator goes to work. And at the end, if we want, we can inspect the resulting output file. And here is also a demo of the same thing with an actual hardware simulation session. We will now show how to use the hardware simulator in order to test an HDL program using a test script. So the first thing that we can do is load the HDL program into the simulator. So let us choose the same XOR HDL chip that we used before. And then instead of playing with the input pins interactively, we can use this icon here to open a test script. And we see that in the Project 0 folder, we have one test script called xor.tst. So let us load it into the simulator environment. Once we do it, this pane in the interface shows us the contents of the currently loaded test script. And we see that it begins with a few comments, and then following that, we see the actual testing commands. And the first command, or the next command to be executed, is highlighted by a yellow bar. We can call it the cursor of the test script. Now, we see that each command ends either with a comma or with a semicolon. And when we click the play icon, the simulator is going to execute all the testing commands until the next semicolon is encountered. Now, the first four commands in this test script set up the simulation, so to speak. And so let us execute them. So I click this icon here, and we see that the cursor moved to the next batch of commands. And this batch says set A to 0, set B to 0. These are the input pins of this particular chip. And then evaluate the chip logic and output the result into the output file. So let us execute this batch of commands. And we see that indeed the A and B inputs are now 0, and the out of the chip happens to be 0, which seems to be right because, as we know, XOR of 0 and 0 should be 0. So let us execute the next batch of test script commands. This batch sets A to 0 and B to 1, evaluates the chips and outputs the result, and indeed we see that XOR of 0 and 1 ended up being 1, which seems to be correct. So executing the next batch of commands sets A to 1 and B to 0, giving the result 1, which also seems to be correct. And then moving along, we execute the next and final batch of commands, which set both A and B to 1, and we see that the XOR responds by emitting the value 0, which once again seems to be correct. Now, the test script for XOR gate is relatively simple because basically it simply executes every possible input combination as stated by the chip truth table. In more complex chips, such an exhaustive testing is less feasible, and therefore the testing scripts will likely be more complex. Now, as we tested this script, the script has also written the results of every test script batch into the output file. You know, this is the result of saying output in the, this is the result of the output command. Now, if you want to inspect the output file, we can do so by going to this control here and selecting output. So let's do that. And once we do it, we see that the output file indeed looks exactly like the truth table of XOR. And this gives us yet another indication that the chip has operated to specification. Before we go on with this step-by-step working example, I would like to stop for a minute or two and say some general things about the general concept of hardware simulators. So first of all, there are many of them. Some of them are free and open source. Others are proprietary and very sophisticated and very expensive. And in this course, we use a simple hardware simulator, which at the same time gives you everything that you need in order to build the hack computer and any other computer that you want to build using the techniques described in the course. So the supplied hardware simulator, which you have on your computer now, is a tool that once again gives you everything you need. And if you want to learn how to use it, there are several places to consult with available documentation. If you go to the Nand To Tetris.org website, you can find a full chapter. I think it's Appendix A, and actually Appendix A and Appendix B in our book describe how to use the hardware simulator, and these chapters are also available freely on the website. And another thing that you should do is go through the hardware simulator tutorial, which is a stack of interactive slides that explain how to use the simulator, as well as all the examples that you saw in this particular lecture. So that's the end of the commercial break about hardware simulators, and we return to our ongoing example. So let us revisit what we have done so far. We looked at a particular HDL file, which records the logic of XOR. We have supplied the simulator with a test script designed to test this particular code. And we also looked at the resulting output file and convinced ourselves that the HDL file is actually correct. Now, this privilege of looking at an output file and saying, yeah, it works, is something which is rarely available in real-life testing. Why? Because the chips that we normally build are far more complex than XOR gate. And there is no way to look at an output file of, let's say, an ALU or a CPU chip or something like that and say, yeah, it works correctly. You know, it's we have to do it in a far more systematic and planned way. So is there a way to do it? Well, you bet. And that's what we're going to do next. In particular, we can carry out the simulation with yet another tool, which is called a compare file. So here's an example of a compare file. It looks exactly like an output file. And in fact, in its previous incarnation, the compare file was an output file of a well-behaving XOR chip. So someone, and we'll talk about this someone momentarily, someone has written an XOR chip correctly, ran it through the simulator, generated an output file, renamed it compare file, and gave it to us and said, now you go and build your chip and compare it to what I did. So basically, we can take the compare file and load it into the simulator, and then start to do the simulation as we did before. And now in each step of the simulation, whenever we output a set of selected pin values, the simulator will compare the output set of values to the respective line in the compare file. And if the two lines will not agree with each other, the simulator will throw a comparison error. So this gives us the ability to not only record the outputs of the chip, but also compare them to desired results. So you probably ask yourself, once again, how do we generate these compare files to begin with, right? Well, we could have left it as a mystery, but there's no need to leave anything unexplained, so here's how we do it. We do it using something called behavioral simulation. In particular, consider this XOR gate that we saw before, and let us assume once again that this implementation is correct, and we put it into the simulator along with the script, we run it, we generate results, and then we simply rename it to be XOR CMP, and it becomes the official compare file of this chip. So what is special about this slide? Didn't we say everything that we said here before? Well, we did, but there's one detail which is remarkably interesting in this notion of behavioral simulation. And the thing which is interesting is that the chip logic can be implemented in any way that the designer wishes. So we can write this chip logic in Java or some other high-level language. We can run the program. We can generate an output file and then, once again, supply it as a compare file. So this technique of writing gate logic using or implementing gate logic using a high-level language gives you the ability to plan and test your hardware before you even write a single line of HDL code, which is, quite a sophisticated way to do things. So we can do everything in high level, and only once the overall design of our machine works properly, we can begin to implement each chip at a time in HDL. All right, so this has been the notion of behavioral simulation, and I want to go on and talk about how we actually carry out hardware construction projects. So the cast of characters in any hardware construction project consists of several players, of which I would like to talk about two. First, we have the system architect. Now, the system architect is the person who is told, go build a chip that supports a certain function of a digital camera or something like that, or go build a chip that monitors a certain medical device. So the architect has the exact sort of user-level specifications of the chip, and the other member in the team is a developer, or more than one developer, or more than one architects, and together they have to design this chip. So how do they do it? Well, the system architect looks at the overall desired operation of the chip, and then he or she makes some decisions about how to break this overall behavior into a set of smaller chips, if you will, or sort of lower level chips. And then for each one of these chips, the architect creates a chip API, which consists of the name of the chip, the names of its input and output pins, a test script, and a compare file. All these things are prepared by the system architect, who may or may not have some people to help him or her in his work. And finally, given these resources, the developers can actually go out and build the chip. So the architecture can do behavioral simulation. They can do whatever they want in order to test that everything fits together nicely. And at some point, the developers actually build this thing using HDL. So once again, that's an example of a well-planned modular design, and yet another example of divide and conquer, taking something very complicated and breaking it into a set of more manageable, smaller modules, each of which can be created and tested in isolation. So, for example, the heck computer, I could have told you something like go build a computer, and actually that's what we do in this course, but we split this job into the construction of something like 30, 30 different chips that together comprise the heck chipset. So we, Noam and I, the course instructors, we play the role of the system architects, and you guys are playing the roles of the actual hardware developers. All right, so the developer's view your view of a particular chip. When we tell you to build a chip, here's what you get. You're going to get a stub file that contains the documentation of the chip that you have to build along with its interface. You're also going to get a test script that we have written for you. You're going to get a compare file, and then, taken together, what you basically got is everything that you need in order to, number one, understand the interface, understand what the chip is supposed to do, the compare file, and we also tell you how we are going to test it. All right, so what do you do with all these resources? Well, what you have to do is write the missing implementation. The missing implementation is the HDL code that should actually drive this entire show. So that's exactly what we're going to do in Unit 1.7, but before we go on to this unit, we also have to say a few things about multi-bit buses, which is a gap that we still have to close in the general description of HDL programming.
In this unit, we'll deal with the question how to deal with a bunch of bits together. Really, this shouldn't really be a whole unit because it's almost trivial, but still, because there is a little bit of technical details attached to it, it's probably worthwhile to spend 5 or 6 minutes on this thing in a short unit. So the basic thing we want to point out is the following thing. When we design hardware, a lot of time we need to manipulate a bunch of bits together. First of all, it's going to be convenient, conceptually convenient, to think about a bunch of bits that are manipulated together as one entity, and allow ourselves to think about it in a slightly higher abstraction level, not of the single bits, but of a bunch of bits together as one entity. The second thing is that, of course, since we're going to describe our chips, our hardware, in hardware description language, of course, we will need some kind of support for that in the hardware description language. So a bunch of bits together that are manipulated together and have one meaning are sometimes called buses, coming from some Latin word meaning many or multiple, something like that. So here's an example of how we can think about that. So when we want to add two numbers, and we will build in the next week, we will build some kind of chip that adds two binary numbers. Each one of these binary numbers will have a bunch of bits, actually 16 bits in our implementation, but we want to think about them as numbers. So our chip that adds two numbers will be described as having two inputs, an A input, which is 16 bits, and the B input, which is 16 bits, and one output, which is the out, which also has 16 bits. So in reality, our chip has 32 wires feeding into it, and 16 wires going out of it, but still it's convenient to think about it as two numbers feeding in and one number feeding out. In this way, we can actually also think about these kind of numbers when we want to use them. So this is how the same chip will be described in HDL. I'm only giving the interface here, the API, and omitting all the internal structure, which is exactly what you learn next week. So we have simply defined our inputs as A and B, and we have in square brackets the number 16, which means that each one of these is 16 bits, very much like the syntax for arrays in programming languages. Now, once we have this kind of notation, we can think about these numbers as entities and manipulate them in higher level chips. So suppose we need to build a chip that now adds 3 numbers, each one of them 16 bits. Logically, we of course know how we can do that. We can just add 2 of them and then add the third one to the sum. So how do we do that? So we get as our interface 3 inputs, first, second, and third, each one of them 16 bits. And we need to have an output, which is just out, also 16 bits. And we want to manipulate it to this level of abstraction, not looking at all the separate bits themselves. This is how we do that in HDL. We have 2 internal chips. One of them adds to 16 bits, adds 16 chips that we've just seen. And we add the first and the second inputs and plug the result into a temporary variable called temp, which is also 16 bits. And then we take this temporary variable and add it to the, or temporary wire if you wish, or temporary bus 16 wires, and add it to the third, getting our final output. And this is how we can just manipulate inside HDL the buses as entities. Now, of course, we should also be able to actually manipulate and get access to separate bits in a bus, because at the end of the day, a bus is just a bunch of bits together. So here's an example of, suppose we want to have a chip that gets as an input a bus bits. So in reality, our chip has 32 wires feeding into it and 16 wires going out of it, but still it's convenient to think about it as 2 numbers feeding in and 1 number feeding out. In this way, we can actually also think about these kind of numbers when we want to use them. So this is how the same chip will be described in HDL. I'm only giving the interface here, the API, and omitting all the internal structure, which is exactly what you'll learn next week. So we have simply defined our inputs as A and B, and we have in square brackets the number 16, which means that each one of these is 16 bits, very much like the syntax for arrays in programming languages. Now, once we have this kind of notation, we can think about these numbers as entities and manipulate them in higher level chips. So suppose we need to build a chip that now adds 3 numbers, each one of them 16 bits. Logically, we of course know how we can do that. We can just add 2 of them and then add the third one to the sum. So how do we do that? So we get as our interface 3 inputs, first, second, and third, each one of them 16 bits. And we need to have an output, which is just out, also 16 bits. And we want to manipulate it to this level of abstraction, not looking at all the separate bits themselves. This is how we do that in HDL. We have 2 internal chips. One of them adds to 16 bits, adds 16 chips that we've just seen. And we add the first and the second inputs and plug the result into a temporary variable called temp, which is also 16 bits. And then we take this temporary variable and add it to the, or temporary wire if you wish, or temporary bus 16 wires, and add it to the third, getting our final output. And this is how we can just manipulate inside HDL the buses as entities. Now, of course, we should also be able to actually manipulate and get access to separate bits in a bus, because at the end of the day, a bus is just a bunch of bits together. So here's an example of, suppose we want to have a chip that gets as an input a bus of 4 bits in this case, and outputs a single bit, which is the AND of all the bits in the bus. How do we do that? To do that, we will need to access bit after bit, and it then simply adds them one after another. And this is how we do that. And notice the syntax, and that's the important thing, the syntax here, when we put an index aside the name of a pin of a bus, we just mean the specific bit that we're talking about. We're using the convention in our HDL that is common to most programming languages nowadays, that a 4-bit bus has bits number 0, 1, 2, and 3. So the indices go from 0 to the bus width minus 1. And this is how we do that. You're gonna, in the next project, in this project, you're gonna have a bunch of chips that actually that's what they do. They take a bunch of bits in the bus and just converge them and just mash them together into a single value, and we call this multi-way chips. So this, we call this kind of chip here, and for way takes 4 bits and ANDs them together. Here's another example showing how we can manipulate bits inside buses, and in the context of another thing we'll do commonly in this week's project, basically taking a bunch of operations and doing them in parallel to each one of the bits in a bunch of buses. So in this example, we have 2 input buses, and we simply want to do a bitwise AND of them. Take the first bit of each A and B, AND it together, and that should produce the first bit of out. Similarly, doing the set for the second bit, and so on. So here's how we do that. We need to have 4 AND gates. Each one of that AND gates performs the operation on one of the corresponding pairs of bits. And we access the bits one after another, simply listing the 0th bit, first bit, second bit, and putting the AND gate on these inputs and producing the correct output. Immediately notice that the 4 bits of the out that we just produced go out as a single bus, because that's how it was defined in the API. So there are a bunch of technical conveniences sometimes that you want to use when dealing with buses. For example, you may sometimes want to break a bus into sub-buses. So the first example here shows what happens if we want to compose a bus, a 16-bit bus, from 2 8-bit buses. So this example shows that we have in our input 2 8-bit buses called LSB, least significant byte, and MSB, most significant byte. And if we want to plug them together into an AND 16 gate, we can just take the first 8 bits of the bus and plug the LSB into it, and the second 8-bit bits and plug the MSB into it. And notice the syntax for doing that. If we specify a subrange inside the square brackets in exactly this format with a dot notation, then we just get the bus being plugged into the correct sub-bus that we want to do it. We can do that on the input, and we can do that on the output, and we can break them in different ways. Now, different hardware description languages deal with all these issues and have different syntactic conventions. And of course, for our hardware description language, which you will need to work with in the project, you can find the exact specification on the website. I would like to say just a few words about some peculiarities, if you wish, on our HDL that you may find convenient to use. First of all, we do allow overlaps of sub-buses. So you can take, let's say, bits 0 to 5 and output them as one bus of 6 bits, and then again take bits, let's say, 3 to 7 and output them as another bus. So simply outputting the same bus in multiple ways that may be overlapping sub-buses. We allow that. Another convention that we have is internal buses are just, their width is completely deduced by what you plugged into them. So you don't need to specify the width of an internal pin. It's just, if it was connected to a bus, it just gets the correct width that it was connected to. And the third syntactic convention that I would like to mention is the fact that if you want to plug lots of zeros or lots of ones into a bus, you can do it together in one command by using true or false as constants, and both of these cases you get are multiplied. So if you plug true into some bus, each one of the bits gets a value 1, and similarly for false, where each one of the bits gets 0. So now we finished this very simple in this week's project, basically taking a bunch of operations and doing them in parallel to each one of the bits in a bunch of buses. So in this example, we have two input buses, and we simply want to do a bitwise AND of them. Take the first bit of each A and B, AND it together, and that should produce the first bit of out. Similarly, doing the set for the second bit, and so on. So here's how we do that. We need to have 4 AND gates. Each one of that AND gates performs the operation on one of the corresponding pairs of bits. And we access the bits one after another, simply listing the zeros bit, first bit, second bit, and putting the AND gate on these inputs and producing the correct output. Immediately notice that the 4 bits of the out that we just produced go out as a single bus, because that's how it was defined in the API. So there are a bunch of technical conveniences sometimes that you want to use when dealing with buses. For example, you may sometimes want to break a bus into sub-buses. So the first example here shows what happens if we want to compose a bus, a 16-bit bus, from 2 8-bit buses. So this example shows that we have in our input 2 8-bit buses called LSB, least significant byte, and MSB, most significant byte. And if we want to plug them together into an AND 16 gate, we can just take the first 8 bits of the bus and plug the LSB into it, and the second 8-bit bits and plug the MSB into it. And notice the syntax for doing that. If we specify a subrange inside the square brackets in exactly this format with a dot dot notation, then we just get the bus being plugged into the correct sub-bus that we want to do it. We can do that on the input, and we can do that on the output, and we can break them in different ways. Now, different hardware description languages deal with all these issues and have different syntactic conventions. And of course, for our hardware description language, which you will need to work with in the project, you can find the exact specification on the website. I would like to say just a few words about some peculiarities, if you wish, on our HDL that you may find convenient to use. First of all, we do allow overlaps of sub-buses. So you can take, let's say, bit 0 to 5 and output them as one bus of 6 bits, and then again take bits, let's say 3 to 7, and output them as another bus. So simply outputting the same bus in multiple ways that may be overlapping subbuses. We allow that. Another convention that we have is internal buses are just their width is completely deduced by what you plugged into them. So you don't need to specify the width of an internal pin. It's just if it was connected to a bus, it just gets the correct width that it was connected to. And the third syntactic convention that I would like to mention is the fact that if you want to plug lots of zeros or lots of ones into a bus, you can do it together in one command by using true or false as constants, and both of these cases are multiplied. So if you plug true into some bus, each one of the bits gets a value 1, and similarly for false, where each one of the bits gets 0. So now we finished this very simple unit about handling a lot of bits together, and now we're ready to actually completely specify the project of this week.
So now that you're familiar with HDL and hardware simulation, we are ready to get our hands dirty and actually go and develop some chips. So in this unit, we're going to give you all the information that you need in order to design the chips that we have to build in Project One. Before we go on, let us remind ourselves what is the general spirit of this course. Well, the story that we're telling you is that God told us, here's a logic gate, NAND, now go and build a computer. And when we asked, how can we possibly do that, God said, one step at a time. And in particular, the hack computer that we are going to build in this course consists of something like 30 different chips, and we are going to build them one step at a time. And in the first project, we start with NAND, which is God-given, or given by us, or you can think about it as some sort of an axiom that you can assume. And using NAND, we want you to build the following gates: NOT, AND, OR, XOR, and so on and so forth. So that's what you have to do for Project One. And why these particular 15 gates? That's a good thing to ask. And the answer is twofold. First of all, every one of these gates is widely used in almost any construction of a digital device, or some version of these gates. And the second answer, which is more practical, is that these gates comprise all the elementary logic gates which are needed in order to build our computer. So Project One lays out the foundation that we're going to use in subsequent projects, because in other projects we're going to use these chips in order to build more complex and more interesting functionality. So once again, here are the chips that we have to build, and I have separated them into three categories, just that we can discuss it in a more organized fashion. So we have some elementary logic gates, widely familiar, NOT, AND, OR, and so on. We have 16-bit variants of some of the logic gates, and we have some multi-way and also multi-way 16-bit variants of the previous gates. And in order to make this all these new concepts more familiar, I will focus on some gates in every one of these categories and say a few words about them. And this, once again, will give you everything that you need in order to build any one of the gates in Project One. So without further ado, let's start to talk about multiplexers and demultiplexers. So what is a multiplexer? A multiplexer is a gate that operates as follows. There are two inputs coming in, and we denote them A and B, and there's a cell input coming in, so-called, from the bottom. Of course, in reality, there's no bottom and left, but I'm talking about this gate diagram here. So three inputs come in, A, B, and cell. What does the multiplexer do? Well, if cell equals 0, the multiplexer outputs A. If cell equals 1, the multiplexer outputs B. That's it. That's the desired behavior of a multiplexer. And here is the truth table of the multiplexer. We have three inputs, so we have 8 different possibilities. And you can convince yourself that the truth table is consistent with what we described before. We can also provide an abbreviated truth table of the multiplexer operation. Once again, if cell is 0, the multiplexer outputs A, otherwise it outputs B. So a two-way multiplexer enables us to select an output one out of two incoming inputs. And this is a fundamental operation that is being used over and over again, both in digital design projects as well as in communications networks. So here's an example of how MOOCs logic comes to play in the context of building what is sometimes called a programmable gate. Now, what is a programmable gate? It's a gate that can behave in one of several different ways according to our will. So here's a simple programmable gate that can act either as an AND gate or as an OR gate. If the select bit is 0, the gate acts as AND. If the select bit is 1, the gate acts as OR. And here's the truth table of the gate, and you can convince yourself that it's consistent with what I said earlier. And here is how I can actually build it. I can use two gates, an AND and an OR, provided, of course, that I have developed them previously, and I can feed the A and B inputs simultaneously to both AND and OR. And we called this before fanning out. So the A input is fanned out into both AND and OR, and the same treatment is done with the B signal. And then I use a single multiplexer to decide, if I want to output the result of the AND or the result of the OR. So the user of this gate that sees only the only the interface of the gate gets exactly what he or she wanted, a programmable gate. Here's the HDL code that implements this particular architecture. And if you want, you can stop the video and inspect this code and make sure that it's consistent with the gate diagram. So here's an example of a MOOCs in the context of a digital design application. How do we build a multiplexer? Well, we get all this information from the system architect, and we also get a stub file. And what we have to do, of course, is to write the HDL code. And it turns out that we can build a multiplexer using 3 gates, AND, OR, and NOT, which we wire in a certain clever way, and the result is the desired MOOCs logic. So it's up to you to figure out how to do the wiring and actually implement the desired multiplexer. All right, moving along, let us talk about demultiplexer. A demultiplexer looks like the inverse of a multiplexer. It receives a single input, and based on the selection bit, it either channels the input to an A output or to a B output. Okay, so it's kind of a distributor of a value into one of several possible channels. In this example, we have it's a two-way multiplexer, so it's a relatively simple example. All the other channels get 0. Okay, and so the DMUX is basically an inverse of a MUX. Of a DMUX is an inverse of a MUX, if you don't like my pronunciation. And once again, it distributes a single input into one of several possible output channels. Once again, just like we said about, what we said about the multiplexer, demultiplexing is also something which is widely used in digital design projects as well as in communication networks. And we're going to get, or you are going to get the stub file, and you actually have to implement the logic in HDL. All right, I'd like to give you an example of how multiplexing and demultiplexing can come to play in the context of communications networks. So here's a typical situation in building a network. And the situation is such that we may have several channels coming in let's say, channels of music or several movies that we want to send over a single communications line. So, the single line that goes here in the middle of the slide can be 5,000 kilometers long, and it may be sort of an underwater line and or a satellite line, and through this single line I want to send multiple messages. How can I possibly do it? Well, if everything is digital, I can put a MOOCs in the sending end of our story, and I can feed the MOOCs an ongoing train of 0, 1, 0, 1, 0, 1, 0, 1. This can be done using what is known as an oscillator. And because the MOOCs is going to get a repetitive train of 0, 1, 0, 1, it is going to output blue, red, blue, red, blue, red. In every cycle, the MOOCs will output, one bit from one of the two inputs. At the receiving end of this story, once again I put a different oscillator, and therefore the DMOOCs is going to distribute the incoming inputs according to the DMOOCs logic. It will output blue, red, blue, red, blue, red, blue, red, and so on. So this logic here, the DMOOCs and the MOOCs logic taken together, enable me to braid or interleave several messages over a single communications line, which may be very expensive, and therefore it pays off to use it for multiple messages. And by the way, another attractive thing about this scheme here is that it can be completely asynchronous, right? They don't have to operate according to a master clock. Every one of these two operations, the encoding and the decoding operations, can be done separately. All right, so we talked about MOOCs and DMOOCs, which were by far the most complicated chips in the elementary logic gates that you have to build. And let's go on and talk about one example of out of the 4 16-bit chips that you have to build. So we'll talk about N16. And N16 looks as follows. We have 2 inputs coming in. Both of them are 16-bit buses, and we have a single 16-bit bus coming out. And basically what we have to implement is a 16-bit AND operation. So it looks like this, right? 1 and 0 should give us 0, 0 and 0 is 0, 1 and 1 finally gives us 1, and so on and so forth. We're going to get 1 if and only if both inputs are 1 in the respective index that we are looking at. Now there's something which is a little bit deceiving in this example here, because the calculation of the logic here is not sequential. Everything is being outputted, boom, in parallel. And this also gives you some tip on how to actually build it, okay? This is a straightforward extension of elementary AND gates. You can read more if you want about how to handle buses of data in HDL. And basically, once you get this stub file, we can implement an AND gate using a set of two-way AND gates. All right, so this has been what I wanted to say about the 16-bit variants that you have to implement. And finally, I want to discuss one example of the multi-way variants, which happens to be actually quite a straightforward notion. Here's an example of a MOOCs 4-way 16. It has 4 inputs coming in. Every one of them is a 16-bit bus. We have a 2-bit selection coming in, and that is because you need 2 bits in order to select 4 different possibilities. And we have the stub file, and we can build this thing using several MOOCs 16 gates, as well as perhaps some other gates as needed. So what do we have to do in Project 1? Once again, we have to implement all these gates, starting with nothing more than NAND and previously designed gates. So, once you built NOT, you're welcome to use it. Once you built NOT and AND, you're welcome to use any one of these two gates, and so on and so forth. So how do we actually do it? How do we actually build every one of these gates? Well, we're going to give you some building materials, and we're going to use XOR as an example. So, you have the gate diagrams from the book or from the lecture. We're going to give you this HDL file, which is available to you, and you can open it up in a text editor. And we're also going to give you a test script and a compare file. And here is the contract that we want you to play with, or to play by the rules of this contract. When you run your XOR HDL, that is, once you take this XOR file and implement it and add your own HDL, when you run the resulting XOR HDL file on the supplied XOR test, the test that we provide, your output file should be the same as the supplied compare file. If this will happen, you have built the chip to our satisfaction. Once again, if your chip generates the expected behavior that we have specified, then you are done with this chip and you can go on to develop the next one. So for every chip that you have to develop, we're going to give you stub file, test script, and a compare file. All right, so the resources of Project One are listed in the Nand To Tetris website. You can look at the different files if you want. And there's no need to download anything, because if you've downloaded the course software suite, then all the necessary files that you need for this project are available in your projects /01 directory, and you're welcome to start working with these files and build Project One. If you need some additional resources, you can look at what we did in the first week, just to sort of get you warmed up for this project. There is the HDL survival guide, tutorial, and the Q&A forum. You can consult with any of these resources in order to gain some confidence and actually go out and build Project One. In closing, I would like to say a few words about what we call the Hack Chipset API. When you build a particular gate diagram like this one, you're going to use all sorts of chip parts. In this case, 2 AND gates, a single OR gate, and 2 converters, or 2 NOT gates. And the question is, how are you supposed to know what are the names of the input and output files, the input and output pins of every one of the gates that you want to use? Well, the answer is that if the gates that you use are so-called off-the-shelf gates, or if they are part of the Hack Chipset API, we provide all the necessary information about how to use them. And in particular, there is a document on the Nand To Tetris website that gives you the API of all the chips in the Hack chipset. This document is actually part of the HDL survival guide. So whenever you're not sure, what are the names of the inputs and outputs pins of a particular chip part, please consult this document and you will know how to use them. Another thing that I'd like to say in closing, before we end this unit, is that you can always use what we call built-in chips. For example, suppose you implement some chip called foo, and you want to use a chip part called bar. How can you do it if you haven't written bar before? Sounds a little bit impossible, but in fact, it is possible. So once again, if you don't implement some chips that are part of the chip of the Hack chipset, you can still use them as chip parts. All you have to do if we gave you the stub file of bar, you have to change the name of this file to something else. For example, instead of calling it chipname.hdl, you can rename it chipname.hdl1. Once you do this, when you load foo into the hardware simulator, the simulator will look for an HDL file that corresponds to the missing chip part, and if it will not find it, it will by default revert to using the built-in implementation of the missing chip. So this gives us tremendous flexibility because it means that in principle we can build these chips in any order that we please, although we recommend that you build the chips in the given order that they are listed in Project 1. So here are some general best practice advice for Project 1 and for subsequent projects as well. Once again, we recommend that you build the chips in the given order because they are specified from the simpler to the more complex. If you don't implement something, you can put it aside and if you want, get back to it later. And you can, if you want, design some helper chips, chips that we haven't specified, which will act like private methods in high-level programming. However, this is really not necessary, and we advise that you don't do it. There's no need to invent any new chips. Just use the chips that we provided, and you should be fine in completing this project. And in general, just like we always do in computer science, strive to use as few parts as possible. Try to create an implementation which is elegant, readable, and well done. Now, I'd like to end this unit with a few notes about frequently asked problems and questions that students raised when working on Project 1. Well, first of all, you have to realize that when you create your HDL program, you have to use some external text editor like Notepad or whatever editor of your liking. You cannot create HDL code using our tools. In particular, you cannot write code inside the simulator. Once again, do it in an external editor, and once you save your HDL file, you can load it into our simulator. The next point that confused some students is that you cannot use a chip as a chip part in its own implementation. There's no recursion in HDL. All right, so all the chips that you use when implementing a new chip have to be some other chips that you've implemented before or some built-in chips which are always available as well. Now, when you run your HDL in the simulator, if everything works well, you will get a message at the bottom left of the simulation saying something like simulation completed successfully. If something goes wrong and if there's a syntax problem with your HDL code or anything like that, you will get an error message printed in red. So once again, some students tended to miss these messages. So pay attention to the bottom left of the simulator when you simulate your chips. Now, in Unit 1.6, Noam explained the whole notion of multi-bit buses. And one thing that we would like to add to this discussion is that these buses are indexed from right to left. So if A is a 16-bit bus, then A0 stands for the rightmost bit, sometimes called the least significant bit or the LSB, and A15 stands for the leftmost bit, also called the most significant bit or the MSB. So this is just a convention that you have to keep in mind when you index your multi-bit buses. And finally, we want to emphasize once again that we provide all sorts of resources with which you can consult when you write HDL code. In particular, the book has a whole appendix dedicated to HDL programming, and this appendix is also available online in the Nand To Tetris website. And there's an excellent document called HDL Survival Guide, which was written by Mark Armbrust. And this is the first place that you have to go to when you get stuck with something and you need some advice. So this has been the end of our unit about Project One overview, and we are ready to go on to the last unit of this week, in which we're going to say to talk about some general observations about elementary logic gates. During the first week of this course, we built a suite of 15 elementary logic gates. And in the next week of the course, we're going to take this basic functionality and use it in order to build some more interesting and powerful chips like adders and arithmetic logic unit. Now, whenever we teach this course, every week of instruction, there's a whole set of issues and questions that come up about different aspects of building hardware and software systems. So we decided to devote the last unit of each week to answer such questions. And we are calling this this last unit every week, a perspective unit. So here are the questions that typically come up at the end of this unit in which we deal with elementary logic gates. So the first question of the day is it possible to build a computer starting with a logic gate other than NAND? Well, I'll take this question. And the answer is indeed yes, it's possible. For example, you can use another elementary gate called NOR, which stands for not or, and base your entire computer on this atomic building block. Likewise, it is quite natural to start with a suite consisting of AND, OR, and NOT gates and use them to build the system. And there are a number of other possibilities. And in fact, it's quite similar to the way geometry can be founded on different sets of axioms. And each one of them can be yet another point of departure to build, all the power and theorems of geometry. This is not such a bad analogy. However, it turns out that NAND gates are very popular in physical implementations of hardware systems because there are many integrated circuit technologies in which it is quite cheap or relatively cheap to build NAND gates. As you well know, during the course, during the first week, we treated these NAND gates as black box abstractions. So the next question, which is directly related to the first one, is, well, if you actually had to build a NAND gate, how would you go about it? Noam, maybe you can answer this question.
Okay, so in this course, we sort of made a point of not going into this question because we feel that is already physics or electronics rather than computer science. But still, let us see an example. There are, of course, many different technologies to implement NAND gates and any other gate, but let me show you the simplest example, if you wish, of such an implementation. So here's an NMOS implementation of a NAND gate. We have a plus voltage, which is going to be 1, our logical 1, and a minus voltage, which is our logical 0. And we're going to connect them as follows. A little resistor here, which is a wick connection, and then two nice transistors, NMOS transistors, which we connect this way. This is going to be our A input, and this is going to be our B input, and this is going to be our output. So these are the two transistors that we have. So how does this implementation work? The basic functionality of one of these NMOS transistors is that whenever the input gate gets high voltage, then it connects the two other terminals. If it gets a negative voltage inside, it disconnects the two terminals. So let's see what happens. If both A and B are 1, then we get a high voltage here, These two terminals are connected. by this transistor. These two terminals are connected by this transistor. So we get a connection all the way from the output to negative. And since this is a weak connection and this is a strong connection, our output is going to be negative or 0. As we want in an AND gate, because when an AND gets 1 and 1 as inputs, it gets 0 as output. In any other case, one of these two inputs is going to be negative, which means a low voltage. The transistor connected to the low voltage input is going to disconnect the two terminals, in which case there is not going to be a connection from the minus sign to the output, and so this weak connection to the plus is the one that's going to rule, and we're going to get a plus output, which is exactly what we want in an AND gate, which is true. So this is a NMOS implementation of an AND gate. There are many other technologies. This one is not used so much anymore since the 70s or 80s. And the important thing in this course is we do not care about the technologies. We do not care neither about this implementation or any other implementation. We want to abstract it away inside of gates that get true and false and output true and false, and we don't care how exactly.
So welcome back from the world of resistors and transistors. And once again, this is a level of detail that we are not going to get into in this course. So here's the next question that we have, and it's about hardware description languages. And the question is, how does the HDL that we used in this course and in this week, how does it compare to real HDL languages that hardware engineers normally use? Well, first of all, our HDL is a very real language because you can use it to design computers and simulate computers, and that's what HDLs are all about. At the same time, obviously, industrial strength HDL languages like Verilog and VHDL are far more complex and powerful than our HDL. Typically, they have a syntax which is some mix of the HDL that we used and something that looks like the C programming language. And they feature all sorts of high-level programming constructs like for and while, which eliminate the need to write a lot of repetitive HDL code. So it's very nice to use these capabilities. And they also feature, like our language does, they feature the ability to model and simulate the notion of time and clocks, without which you wouldn't be able to build sequential logic. Logic that ends up with which you end up building things like memories and counters and so on. So these languages are very nice, and at the same time, they are quite complicated, and it would take you at least a month or so to master these languages in order to begin writing some code for this course. So as an alternative, Noam and I decided to design a very simple dialect or a very simple version of HDL and offer it to you. It has all the capabilities that we need in order to build the computer that we build in this course, and you can learn it in 1 hour. The next question, which is for Noam, is as follows. The chips that we built so far were quite simple. How does one go about designing complex chips containing hundreds of parts and connections?
Well, the truth is that there is no simple general way of designing complex circuits. It's really a complicated design challenge, and you need human ingenuity to do it well. Now, there are many techniques that you learn in digital circuit construction courses. For example, there are techniques called Carnot maps that allow you to optimize gates with a small number of inputs. Sometimes you can use various tools. For example, there are so-called silicon compilers where you specify what's the functionality that you want, and the silicon compiler already has inside it a lot of logic and a lot of algorithms that can optimize gates for you. But again, it is not perfect algorithms. These are all heuristics because the general problem, the so-called NP-complete, you cannot find a computer program that does it perfectly. The real answer is that after all these tools and all these techniques and so on, at the end of the day, you use the usual tools of computer science, modularity and abstraction. You break a complex problem into simpler parts, and the simpler parts are simpler to optimize and to construct. And at the end of the day, after you use all your tools, after you use all your techniques, you go back and use this modularity idea.
So these were the questions that we chose to focus on in this first perspective unit of week 1. As you can see, this particular format of the perspective unit is open-ended. There are numerous questions that can come up. Once again, we don't want to deal with the level of transistors and resistors. You know, this is something that belongs to electrical engineering. We want to focus on computer science. And when it comes to hardware technologies and so on, there are many questions that Noam and I cannot answer either. So we welcome any questions that can come up. You can post these questions on the course Q&A forum. And if there are other students who have some knowledge about these areas, you are perfectly welcome to go to the Q&A forum of the website of this course and answer these questions on your own.